Alright, so for the first part here of homework 1-3, we'll hopefully get through maybe the first half or so. So if an object is accelerating towards a point, then it must be getting closer and closer to that point. I think and hope most of you guys would have nailed this one right. This is false. So just to give you a quick illustration, if my point was over here and the object was over here but moving away from that, so the velocity was initially moving away from that, then even if the acceleration was maybe pulling back towards that point, the object would only initially be slowing down until eventually turning around and moving back towards that point. But just because the acceleration is pointing that way doesn't mean the object has to be getting closer to that, right? The object would actually still be moving off to the right until it slows down and turns back around. So in this case, again, that's false. It doesn't have to accelerate towards that point. Example 2 here, hopefully not too bad. There is maybe one or two little tricks to this question, so just make sure you're paying close attention. But the figure shows the positive or the position of an object moving along a line here, so it's giving us a pretty standard motion diagram, right? The only thing that they don't show us that normally I would encourage you to show us would be the velocity vectors as well, right? So if I was drawing those velocity vectors in, maybe they would be doing something more or less like that. But otherwise a very standard motion diagram. So of these options, the object is accelerating to the left, the object is accelerating to the right, the acceleration of the object is the same direction as the velocity, and the average speed of the object is 1.0 meters per second. Really, B and C are very similarly linked. The object is definitely moving towards the right. Do we agree? Because every second time it's moving further and further to the right. So if the object was also accelerating to the right, or if it was accelerating in the same direction that it was moving, wouldn't the gaps be getting bigger over time? Right? If I'm moving this way and also accelerating that way, then I would expect my velocity to be increasing, and so the spacing between these dots should be increasing. So based on that fact alone, we can rule out B and C, and then obviously that fact again really includes A as my best option. So the fact that even though I'm moving to the right, because I'm slowing down, the acceleration has to be towards the left. If we're slowing down, the acceleration is opposite to the direction in which we're moving. So option A is the best answer. The one aspect you do have to be careful about then for part D is to find the average speed. Well, if I look at the average speed, I go a total of 6 meters. The thing you have to be careful about is the total time that it takes me to go 6 meters is not the full 6 seconds because I started at 1 second. So even though my velocity, my average speed here, even though I do go 6 meters, I do so in only 5 seconds. So my average velocity would be 1.2 meters per second and not 1. So again, option D we can rule out as well. So option A is our best choice for that second question. Question 3 here, I actually originally read this incorrectly, and I thought they were asking us for the position, but they're asking us for the velocity in the x direction as a function of time. So they're asking us about the velocity as a function of time. So an object is moving with a constant non-zero acceleration. So let's think about what that means in terms of an acceleration versus time graph. So if I've got my acceleration up here and my time down here, it is a constant, but it's not zero. So the acceleration is not down here, but it is constant. So the acceleration would be just a horizontal line at maybe wherever we want that to be, right? So I'll just call this C for whatever constant value we want. The significance here, though, right, is the acceleration is the slope of a velocity versus time graph. And so if the acceleration is constant, then the slope of this graph, no matter where it starts, the slope of this graph better be constant as well. So my velocity versus time graph should make a straight line graph making an angle with the x-axis, or with the time axis. Okay, so option C is my best option here. If it was asking us for the position versus time, we could say it's a parabolic curve, but they're only asking us for the velocity versus time. How do I know that the velocity is not just a horizontal line, right? How do I know that the velocity doesn't just do this? Well, the slope of that graph would be 0, and they told me it was the acceleration was non-zero. So that's how I know it's not just a horizontal line, and graphs really don't make any sense to be a vertical straight line, because that's assuming that you are doing so without the passage of time. If you figure that out at some point, let me know, because I'm sure we could get into the money-making business if we could figure out how to stop time and have a velocity. But anyway, option C hopefully makes a lot of sense for this question. So with questions 4 and 5 here, I got a little ahead of myself. We will talk more about free fall and that type of stuff after our quiz. But this should be mostly a review, right? For those of you that had this course from me last year, this should be a review. So two objects are thrown from the top of a building and experience no appreciable air resistance. One is thrown up, the other one is thrown down, both with the same initial speed. What are their speeds when they hit the ground? Well, the key concept here, if I take an object and I throw it upward, if there's no air resistance, then by the time that it reaches the same location, it's moving at the same velocity, it's just now moving downward. So if I threw it upward with a speed of 10 meters per second, by the time it reaches that same height, it's also got a speed of 10 meters per second. So regardless of whether I initially throw the ball upward at 10 meters per second or downward at 10 meters per second, by the time it reaches the level of the building, it's moving downward at 10 meters per second. And since at that point they're then falling the same distance and hitting the ground in the same amount of time, both of those balls would be traveling at the same speed. So a very important concept, but like I said, we will revisit this concept in class once we cover this material. So I got a little bit ahead of myself. Similarly, on question 5, two objects dropped from a bridge. Again, this is an example of free fall, but the reason that this one should be hopefully one that we can conquer here is we know that if something is free falling, if something's falling due to gravity, that the gravity is constant at 9.80 meters per second squared. And how did we first define acceleration? Well, acceleration equals change in velocity over time. So this question is asking me as time progresses the difference in their speeds, so in other words the difference in their velocities, right? Well, with each additional second the velocity should change by the same amount regardless of when the ball was dropped. So with each additional second as time passes, the velocity still changes by the same amount for each of them. So the difference in their speed would remain constant. Now the one that I dropped first would have a velocity head start over the other one, right? So after 1 second, this one is already moving at a certain speed, whereas this one is moving at rest. So we would define it maybe as something more or less like this, right? But the difference between those two velocities remains constant as they continue to fall. Again, we'll revisit this a little bit more, but hopefully that was one that most of you from last year feel comfortable with. If not, shame on you. But hopefully that did feel pretty good. Anyway, so this example, another one like we've seen a few times now, going back to the first few homeworks, they ask us to find the instantaneous acceleration and to find the average acceleration. So they give me a position function, I just have to plug in the variables, and I'll go ahead and do this like I said I would. I will write you the correct answers up here. So for part A, you should have gotten 43.84 meters per second squared. And for part B, for the average acceleration, you should have gotten 17.9 or thereabouts meters per second squared. Okay, so again, I'll go ahead and write those up here. If you got those and you're confident with those, skip this and skip on to the next question. For those of us that didn't get those or just want to review this a little bit more, right, I'm going to start with my position function by just plugging in the variables they gave me. So 3.6t cubed minus 4t squared plus 60t minus 7. Okay, so that's my position function. If I want to find the instantaneous acceleration, I need my acceleration function. So to go from the position function to the acceleration function, I have to do the derivative twice. So the first derivative here would be my velocity function. So when I do the power rule, I bring the 3 out front, I multiply it right, reduce it by 1. So I know you guys hopefully are getting comfortable with the power rule by now. This would become t to the 0th power, and then that would just go away. So this would be my velocity function. Again, that's the first derivative, so if you want to think of that as x prime of t. Then the derivative of the velocity function is my acceleration function. So then if I do the power rule one more time here, so 21.6t minus 8, and again t to the 0th power, and now my 60 has gone away. So for part A, if I want to find the instantaneous acceleration at 2.4 seconds, I simply take my acceleration function and I plug in 2.4 seconds. So 21.6 times 2.4 minus 8, and that is where I got my 43.84 meters per second squared. Okay, so hopefully that part wasn't too bad, right? Finding the instantaneous. part B, however, we do need to be very comfortable with this. I know if you've seen the videos, I've emphasized this a few times already, but to find the average acceleration, I actually do not want to use the acceleration function. Instead, I want to use my definition for acceleration, or for average acceleration, which is my change in velocity over my change in time. So instead of using the acceleration function, what we're going to do is we're going to take our velocity function and plug in 2.4 and plug in 0 and see what our change in velocity is. So the velocity of 2.4 seconds, again I'm just plugging in 2.4, so I do 10.8 times 2.4 squared minus 8 times 2.4 plus 60, and my velocity at 2.4 seconds, I calculated that to be 103.0. Okay, so my velocity at 2.4 seconds is 103. Do the same thing for the velocity of 0, and keep in mind it is not 0 in this case, right? So as I plug in 10.8 times 0 squared minus 8 times 0 plus 60, right? Those two obviously cancel out, but I still do have 60 meters per second. So in this case, I've got my two velocities. I just want to find my average acceleration by finding the change in velocity over time. So my average acceleration, the final velocity here at 2.4 seconds of 103 minus my initial velocity of 60 divided by the time, so the time again was just 2.4 seconds. So I get 43 over 2.4, and that's where I got my previous answer of 17.9 meters per second squared. Okay, so again, the biggest emphasis here, to find the average acceleration, you do not use the acceleration function, you use the velocity function and you find your two values and then the change in those two values. So hopefully this helps them on question 6. Question 7, I messed up because I gave this question to you on the previous homework assignment. So hopefully you were able to look at this the second time and do it with ease. But if you do need to go back, I think this was question maybe 6 on the previous homework. I don't remember verbatim, but this was actually in the second homework assignment as well. So I'm not going to work all the way through it, but I'll write down the correct answer. So 4/3 t cubed plus 3t plus 1. Okay, so again, this one hopefully a pretty easy question. I messed up by giving it to you twice. I'm going to go ahead and stop the first video here, and then we'll pick up with questions 8, 9, and 10 for part 2.